Okay, hello. So we're now on rigid object in equilibrium. So this is a continuation of the discussion about the torque. So for today, we will be covering net torque as well as the center of gravity. Uh, we have covered the torque from the previous discussion. But then, although we solved for net torque before, this time around, so let's say we imagine an object that can rotate, but it is exhibiting no translational acceleration. So that means it is in equilibrium, so there's no translational acceleration or no rotational acceleration. So such an object is in both translational and rotational equilibrium. So therefore, the net force and the net torque about any axis are both equal to zero. So the summation of the forces on the x-axis as well as the summation of forces on vertical axis will be zero, as well as the summation of torque at a certain reference point will be equal to zero as well. So that is a rigid body in equilibrium. So usually, so if you are given certain object or multiple particles, and then we want to determine the center of gravity, so the center of gravity then, so based on the x and y point, so can be computed using this formula. So we're in m sub 1, m sub 2, and m sub 3, so would correspond to the mass of the object, and the x sub 1, x sub 2, and x sub 3 would be the x component. So if we are going to find the y coordinate, so we just simply change the x into y. So in short, the x component of the center of mass so would be the summation of m sub I multiplied with x sub I. So we're in I starts at 1. And then so divided with the summation of m sub I. So the center of gravity, so similar with center of gravity, so the centroid could also be found so using the same formula. So the only difference is instead of getting the mass, so we are exchanging that one into the area. Okay. However, the x sub 1 there so corresponds to the x coordinate for the centroid, just similar to the given figure. So for centroid, okay, so for centroid, instead of a mass, so we exchange this one into the area. So that is how we get the centroid usually for complex uh, figures, composite figures. So to better understand, so let's have this example. So the first example is that we are given a seesaw, okay, so consisting of a uniform board of mass m and length. Okay, so as you can see here, uh, so let's say uh, I'm going to give a value for the mass. So let's say the mass of the board is around uh, 40 kilogram. And then supports at rest a father and a daughter with masses of 75 kilogram, and the mass of the father is 75 kilogram. So we have the mass of the father here, which is 75 kilogram. So the mass of the board, so usually, so since the board is rectangular, then the mass, okay, so will concentrate, or the weight will concentrate at the center or at the centroid of the given object. So in this case, so the mass is assumed. Okay. So I included the mass there, so which is 40 kilograms. So we could have a numerical constant. So for our answer, and then the mass of the daughter is equivalent to 32 kilogram respectively, as shown in the figure. So the support, so which is called the fulcrum, is under the center of gravity of the board. So the father is at a distance d from the center, and the daughter is at a distance of 2.5, let's say 2.5 meters. So this is 2.5 meters, so from the center. So determine the magnitude of the upward force N, so exerted by the support on the board, and determine the father or where the father should sit so to balance the system at rest. So for our free body diagram, so we can draw a line. So let's say, so we have forces going downward. So this is the fulcrum. I'm just assuming. So if we have the mass of the father, so we can compute for the weight. Okay, so later on. And then we have the mass of the daughter. So we have the weight of the father, so to be mass of the father, so multiply it with the gravitational constant. So the mass of the father is 75 kilogram. The gravitational constant is 9.8 meters per second squared. So thus, so providing the weight, so to be equal to 75, so times 9.8, so that is 735 Newton. So while the weight of the daughter is 32 kilogram, so multiply it with 9.8 meters per second squared, so giving us a 32 times 9.8, so 313.6 Newton. So while that of the board, so the mass, so for the mass of the board, so which is equal to so for the weight of the board, so it's mass of the board, so times the gravity, so that is 40 kilogram, so multiply it with 9.8 meters per second squared, so which is equal to 40 times 9.8, 392 Newton. So our task is to find the normal force. Okay, so in between the contact. And at the same time, so if the distance here is equivalent to 2.5 meters, so what would be this distance d? So for our requirement, so we are to find the n and then the distance as well. So where the father would sit, so to make this one balance. So based on, to make this one balance, so we can use the two assumption that the vertical forces, summation of vertical forces is equal to 0, and at the same time, so the summation of the torque, okay, so along the, or the summation of the torque at the fulcrum, so will be equal to 0. So since we have already the masses, okay, so we can compute for the normal force. So that is, so we find the summation of vertical forces, and that would be equal to 0. So anything upward is considered positive. So in this case, that is n, and then anything downward so will be treated as negative. So therefore, that would be minus weight of the father minus weight of the board, and minus weight of the daughter is equals to 0. So therefore, the normal force is just weight of the father plus weight of the board plus weight of the daughter. So that is equal to, weight of the father is 735 Newton, weight of the board is 392 Newton, and weight of the daughter is 313.6 Newton. So adding that up, so giving us, so 735, so plus 392, so plus 313.6, so giving us a 1,440.6 Newton. So that would be the normal force, okay? So that will be exerted by the fulcrum. And for the second one, so we can take the summation of the torque. So the summation of the torque, so can be taken at different points. So we can take it at any of the point, okay, so which involve force. And so since torque is the product of the perpendicular force, so multiply it with the lever arm. So if we are going to find the summation of torque at a certain point, so which consists of forces, then it would just cancel out. Like for example, if I'm going to take a summation of torque at the fulcrum, in this case at this given point, so that means the lever, since the normal force and the weight of the board is exactly at the fulcrum, and there is no lever arm. Okay, so there's no lever arm. So for the normal force and that of the weight of the board, so therefore the torque will be 0 at the fulcrum. So based on the normal force and the weight of the board. So unlike with that of the weight of the father as well as weight of the daughter, okay, so weight of the daughter, so there will be a lever arm, okay. So the weight of the daughter is 2.5 meters. So from the fulcrum, so therefore the lever arm there is 2.5 meters. So while that of the father, so the lever arm is equivalent to D. That is what we are going to find. So therefore, so we'll be finding the summation of torque, and that would be equal to 0, and then our reference would be at the fulcrum side, or at the fulcrum point. So at the fulcrum point, so we considered again the torque to be positive if it is counterclockwise, and then if it is clockwise, that will be negative. So in this case, so the weight of the father, So it's will be moved counterclockwise to go. Okay, so this would be the case here. So counterclockwise. So from the weight of the father going to the fulcrum point, and unlike that of the weight of the daughter, so that would be clockwise. So to proceed to the fulcrum point or to the fulcrum of the seesaw. So in that case, so that would be the torque or the so the torque is just equal to the force multiplied with the distance. So in this case, so that would be the weight of the father, so multiplied with d. And since that is a counterclockwise, so that makes it negative. And then minus the weight of the daughter, so multiply it with the distance, so which is 2.5 meters. And since that's summation of the torque, so that would be equal to 0. And then, so we are given the weight of the father, so to be 735 Newton. And multiply it with the lever arm D. And then minus the weight of the daughter is 313.6. So multiply it with 2.5 meters is equals to 0. So thus we have a 735D is equals to, so we multiply, so 313.6, then we multiply it by 2.5. So giving us a 700. So we transform it at the right side. So we have a 784, and that is in Newton meter. But then, so the distance will be 784 all over 735. So therefore, the father should sit. So 784 divided with 735, that is 1.07 meters. So that is how far the father should, or how far from the fulcrum, so the father should sit, so to balance the weight of the daughter, which is 2.5 meters from the fulcrum. So that is our example number 1. So for example number 2, so we have a mobile that is constructed of light rods, light strings, and bits souvenirs as shown in the figure. If mass 4, okay, so that's a coral, is 12 grams, so find the values for M1, M2, and M3. So to solve for this one, so we will start at the so we do it. So there's no weight so given for the rod, so we treat it as 0. So let's say we start with so the first FBD, so we have 3. So 1, 2, 3, and then 4, 2, 4. Then we are given a mass 4. Then would be, this is our origin or where the string is attached. And that is mass 1. So mass 4 is 12 grams. And then mass 1 is equal to unknown. Okay. And then of course, so we have the tension of the string. So given that the rod, Okay, and the string will have negligible mass. So to find M1, so we can do so the requirements are M1, M2, and M3. So we do the summation of torque. So to make this one balance, so should be equal to 0. So that is we just get the weight. Okay, so let's say this is the weight for W4, and this one is the W1. So the torque then so would be equal to the weight 4, and then the distance is 3 centimeters. This one is 4 centimeters. So this is weight 4, so times 3 centimeter. But then, so 1 meter is 100 centimeter. And then that is counterclockwise, so that makes it, okay, so this one is counterclockwise. And then this one would be clockwise. So this is positive, this would be negative. And then, so that is minus W1. So times 4 centimeter. So times 1 meter all over 100 centimeter is equals to 0. So our weight force so can be computed as 12 grams. So we're in 1 kilogram, so would be 1,000 grams. And then the gravity is 9.8. And then we will be transposing W1. So W1 so would then be so mass 1. So multiply it with the gravity. Or something missing. So 3 centimeters. So weight of the coral there is mass, multiply it with the gravitational constant, or this is just the mg. So we multiply it with 3 all over 100, so will be 0.03. And then this time this would be in meters. And it's equals to the weight of the first object, so would be mass 1, so times 9.8 meters per second squared. And then we multiply it with 0.04. So therefore, so this one would just canceled out. And then, so we'll have this one is in meters already. Then kilograms. So this would be in Newton meter. Okay. So 12 times 3 divided by 0.03. So 0.03 times 12 divided with 1,000. So that would be 0.00036, and is equal to M1 as 0.04. So the mass then will be 0.0036 divided with 0.04. So that makes it 0.009 this time. So that would be in kilogram. And 1 kilogram is 1,000 grams. So therefore, mass then will be 0.009, so times 1,000, so we have 9 grams. So our mass number 1 is 9 grams. So will that be the same then? So 12 times 3 is 36. Then 9 times 4 is 36. Okay. So therefore, so let's say I'm going to designate this one as T1. So T1 then, so summation of, if we take the summation of vertical forces, which is equals to 0, so T1 then, so minus W4 minus W1 is equals to 0. So therefore, T1 is W4 plus W1. So we're in W4 so will be in that case, so that would just be 12, so times 9.8, and then plus the weight is 9 times 9.8. So T1 then will be 12 times 9.8, so plus 9 times 9.8, so which is 205.8 Newton. So in terms of the mass, or that is M14, so the mass then will be equal to 205, so divide with 9.8, that is 21. 12 plus 9 is 21, so 21 grams. So since that is 21 grams, so we can now get the M2. So 2 centimeters and 5 centimeters. So this one is equivalent to M14. So this is M14, so which is so M2 is unknown, so M14 is given, so which is 21 grams. And then we have given the tension 2. So this is 2 centimeters and this is 5 centimeter. Okay, so if we're not going to convert, so the same as true, so would happen. So we take the summation of the torque, and that is equal to 0. And in this case, it's just the weight 2 multiply it with 2 centimeters, and then so minus the weight 1 4, so multiply it with 5 centimeters, that would be equal to 0. But then weight 2 then, so times 2 centimeters is equals to weight 1 4, so times 5 centimeter. So weight 2 is just M2, so times G, so times 2 centimeters equals to M14, so times G times 5 centimeter. So G would just cancelled out, and M2 can then be computed as simply, so M14, so multiply it with 5 centimeters, divide it with 2 centimeters, and that makes it mass 2, so M14 is 21 grams, multiply it with 2.5. So 21 times 2.5, so that makes it 52.5 grams. So then we can get tension 2. So similar, so we are going to find the summation of vertical forces, so to be equal to 0, and that makes it, so T2, so minus W2 minus W14 is equals to 0. So tension 2 then is just weight 2, so plus weight 1 4. So this is mass times gravity. So the mass there is equivalent to 52.5 grams. So 52.5. So grams. So since that is grams, so I'm just going to divide it with 1 kilogram to be 1,000, and then multiply it with 9.8. So plus 1 4 is 21 grams. Multiply it with 1,000. So multiply it with 9.8. So our T2 then is 52.5. So multiply it with 9.8 over 1,000. And then plus 21 times 9.8 divided with 1,000. Oh, sorry. So T1 here is not 205.8. So since we haven't divided that one by uh, so T1 here, so I'm just going to change the unit. So the unit here is just gram meter per second squared. So my objective here is just to find so what is uh, the mass. Okay, so the mass at the center. Okay, so which is the combination of the two. So T2 then. So I'm just going to follow what I did at the top. So we multiply it with 9.8 plus 21 times 9.8. So T2 then, so will be so 52.5, so times 9.8. 9.8. So plus 21 times 9.8, which is 720.3. And this would be in grams meters per second squared. So our T2 then, it's the same as our M 1 to 4. So it's a combination. So we divide this one by 9.8. So that is 73.5. I just add the 2. 73.5. So that is why lastly, so 4 centimeters. So the mass 1 to 4 is 73.5 grams. And then so we have 4 centimeters. So this would be the point. And the other one is 6 centimeters. So 2, 3, 4, 5, 6. So this is 4 centimeters and this is 6 centimeters. And this is M 1, M3. Okay, so again, so if we take the summation of torque at the origin, so in this case, this is the origin, this is the origin here. So that is just, this is clockwise, positive, counterclockwise, negative. So that is just simply the mass of 1 to 4, so times G, and then times the distance, so which the distance or the 4 centimeter distance, and then minus M3, so times G times the 6 centimeter distance, which is equal to 0. So G will be cancelled out. And then we have M124, so which is 73.5 grams. And then 4 centimeter is equals to M3 times 6 centimeter. So we divide both sides by 6 centimeters. So which would cancel that out. And therefore, M3 will be equal to 73.5. So times 4 divided with 6. So we have 49 grams. So M3 is 49 grams, M2 is 52.5, and then M1 is 90. So that's how we find the masses. Okay, so for the given problem. So let's have our last example. So this time, so we are to locate the center of gravity. So to locate the center of gravity here, so we will be using the same formula for the center of mass. So in this case, so we are to find, so the requirement, so would be the X and Y. So that would be the X component of the center of gravity, and then Y is the Y component of the center of gravity. So to do this one, so there are actually two ways on how to do it. But then, so if that is 4, 9, okay, so let me redraw this one. So for the solution, so I'll do it, this would be per 1, 2, 3, 4, 5, 6, 7, 8, 9. So one box will correspond to 2 centimeters. So this is 4. And then we have a 4 as well. The length is 12. So this should be 6, 2, 4, 6. So to find for the center of gravity, so we can divide this one as either we're going to treat this one as, so this is considered as the area 1, and this is considered as the area 2. So we can compute for the area 1. So if this is 4 centimeters, so this is 4 centimeter. This is 18 centimeter. This would be, so 4, 4. That is 12. So 12 minus 4 is 8. So this one is 8 centimeters and this is 4 centimeter. So we can now compute for area number 1. So area number 1, so it's just simply the length times the width. So the length is 18 centimeters. So multiply it with 4 centimeters. So 18 times 4, 36, 72 square centimeter. And then for the second area, so we have the length, which is 8 centimeters, so times 4 centimeter. So 8 times 4, 32 square centimeters. So to get for the X component, so we have to identify, so what would be the X sub 1. So since there is the center for area number 1, so will be, so this is the given line, sorry, and then the center, so 18, that would be 9. So therefore this distance, so would correspond to our x sub 1, and then the distance, so from here to here, so would correspond to y1. And then, so for the other one, so the center, so this is the center, and this one. So our x2 then, so from the origin, so this is considered as the origin. So as you can see here, so x1 is 2 centimeters. So x2 is 9, or y1 is 9 centimeter. So our x2 then, so will be, so 4, 6, 8. Okay. So x2 natin, so will be, so 2, 4, 6, 8. So 8 centimeters. So while that of our y2, so y2 is equals to 2 centimeters. So now, so to get for the x component, so that is just simply x sub 1, so multiply it with the area 1, plus x sub 2, multiply it with area 2, so divide it with area 1 plus area 2. So x sub 1 is 2 centimeters, so area 2, or area 1 is 72 centimeters square. So plus x sub 2 is 8 centimeters. So while the or the area 2 is 32 centimeters, square centimeter. So divide it with the two areas of 72 centimeters square plus 32 centimeters square. So the x component then, so will be, so 2 times 72, so plus 8 times 32, so divide it with 72 plus 32, so which is 3.85 centimeters. So for the x. So for the y, so the y component then, so will be y1 a1 plus y2 a2 all over a1 plus a2. So y1 is 9 centimeters. So area 1 is 72 square centimeter. Plus y2 is 2 centimeters. So times 32 square centimeters. So divide it with 72 square centimeters plus 32 square centimeter. So y then will be 9 times 72. So plus 2 times 32. So divide it by 72 plus 32. So which is 6.85. So that's the centroid then. So will be 3.85. And then it's 6.85. So 2, 4, 6. So approximately. So this would be the center of gravity. So that is the center of gravity, which is approximately 3.81 and 6.85. And that's it.